Hello, everyone. My name is Jared Longfox, one of the co-hosts of this AIAA Education and Outreach Space Resources webinar series. Today, we're lucky enough to have Dr. Nerma Caluk with us from Skidmore, Owings, and Merrill, SOM, to discuss various aspects of lunar civil and structural engineering. Nerma got her PhD in structural engineering from Florida International University in, what was it, 2019?
PhD 2023, 2023. Yeah.
My bad. 2023. So, cool. Anyway, sorry about that. So I will hand it over to Nerma, but I do want to say if you guys have questions and comments, as always, you're encouraged to punch them in the Q&A as we go. We're going to answer them at the end in the order they were received, as always. If you have any technical difficulties, you can also punch that in the chat if you are able on the attendee side or in the Q&A, and I will see it. To save some bandwidth, my camera will be off, but I will be here. So thank you all for coming, and without further ado, take it away.
Thank you. Okay, I'm going to start sharing. Can you see the main presentation?
Yep,
I think so,
I
yeah.
can. That
Okay,
looks great.
awesome. Sounds good. Yeah, so first of all, Jared, thank you so much for having me here. This is very exciting. And I think we talked before when I said that before you reached out for me, inviting me to present, I was actually talking about this topic with my supervisor here. I'm like, yeah, we should discuss this and make a presentation just so we have it out there, and then we might present it internally or whatever is needed and so on. So, and then Jared reached out a couple of days later. I'm like, oh my God, this is perfect opportunity right now. So, yeah, so my name is Nerma Caluk. I am a structural engineer at SOM in our San Francisco office. I've been here working for the past couple of years now, almost 2 years right after my doctorate at FIU. I had a great opportunity there to work with a couple of people from SwampWorks and provide some input there and dig into the lunar research, which was so exciting. And yeah, I hope I can provide some insights to everybody here and whoever else needs any questions. So today's presentation isn't going to be very technical, which I'm used to giving technical presentations, but I want to provide like a global vision of how do we approach design, engineering, and the construction on the lunar surface, and hopefully other entities, other areas as well. So like on Earth, for example, if something goes wrong on a job site, we got OSHA. I think some of you are familiar with OSHA. We got RFIs. We have lunch trucks nearby as well. But on the moon, there's really nobody to call and not a lot of margin for error. In space, this OSHA cannot actually hear you because we're in vacuum. So we have to design like our lives depend on it, literally. So this isn't just construction. It means it's survival and sustainable human presence, and it means that we need to kind of rethink everything now as we design, analyze, and build as well. So today we're going to explore how architecture, structural engineering, and robotics kind of come together not only to meet these challenges, but to unlock a new era of structural innovation that can thrive in some of the most extreme environments imaginable. And today I'm going to focus more on the lunar infrastructure and lunar environments and load, but similar approach would probably apply to other environments like, for example, Martian. So next slide, let me see. Okay, so before we dive in and talk about how robots build stuff on the moon bases and so on, I want to talk about how we build things here the old-fashioned way with blueprints, scaffolding, rebar, and very, very importantly, an unhealthy amount of coffee on construction sites. For thousands of years, the terrestrial construction has been defined by this interplay of the human ingenuity, craftsmanship, and this dynamic relationship between the conceptual design and practical execution. From the limited shelters of earth that we have here that are made of earth and stone to the sophisticated structures made out of steel and glass that kind of define our skylines today, especially if you're living in the urban areas, our methods have continuously evolved, translating this abstract architectural concept into a tangible reality. So central to this process is a system of documentation, and I think some of you are familiar with, including the drawing plans, sections, elevations that communicate this architectural vision, structural logic, and sequence of construction. These documents don't just describe a building and how it looks like. They coordinate this choreography between the designer, engineer, and the builder as well. So on Earth, the structural components are laid out based on these drawings, carefully measured and executed by team of skilled laborers. And I think some of you are probably using the robotics drawings as well for different component assemblies or for assembly of rockets and drawing plans and so on. But a good example is this is one of the, I think it's this slide, yeah. So one of the examples is a building that I'm currently working on, a couple of them actually, 5 of them on one of the in Santa Barbara. And this is just a couple of them showed here. It's a perfect example how we're trying to look into these plans, understand where the studios are, where the bathrooms are, where the stairs are, how everything kind of coordinates together, lay out the shear walls, running millions of iterations by 5-inch length or shortened shear walls, where the link beams will be located, and so many other things and components that are laid out on these plans, providing for so much information for the actual humans to build these structures on site. But in order to build a site, we need the temporary infrastructure, like scaffolding, cranes, formwork, and so on, which serve as the physical framework that allows the building to emerge piece by piece. And adjustments and improvisation do happen in real time. Like, for example, if we have a steel column can be shifted to fit in an anchor bolt. We have a rebar cage that has to be modified due to unforeseen congestions. We built not just with precision, but with the tolerance for error, because the human workforce is always present there, and it's present there to adapt. So sometimes the most critical tools isn't just a BIM tablet that we have on site or a laser that we have to measure certain things. It's the experience of the construction worker. It's the tape measure that we can use. It's a roll of duct tape. So it all depends. Construction is rarely as clean as the renderings, as you probably already know that. But sometimes it does look like an actual rendering. It's been a couple of projects that I'm like, I don't know if this is an actual rendering or we actually built the structure. But it represents an art form of orchestrating a controlled chaos. And I like this. The next sentence is kind of, in many ways, we're building buildings on Earth, not just for construction, but they're kind of negotiated into place. That's how we approach these things. And over the last couple of centuries, these processes have evolved dramatically. Buildings have pushed these limits not only in scale, but also in complexity. And this is an example that I can, on the screen, you can see the Al Hamra Tower in Kuwait, which it's a sculpted high-rise with a spiraling and carved form that requires an asymmetric load-bearing wall system, thickening dramatically along these tower spine and going up all the way at, I forgot how many meters this is. It's a high one to counteract the lateral forces. And each floor plate is actually slightly different, demanding this high precision layout and curved framework, which is executed by human workforce, guided by both the digital and tactical experiences. Another example is the London's 201 Bishopsgate. We see this interplay of these large span steel frame and complex double curved facade systems. Took some time to say that full sentence there. The steel die grids weren't just structural, that you can see here. They were designed to accommodate these architectural transparency and pedestrian scale, demanding a very close collaboration between the architects, between the structural engineer and the facade consultants through the actual build. In addition to this building being located on rail tracks, so there's a lot of load combinations and load cases that had to be addressed. Additionally, the tolerances were adjusted on site, connections were being hand aligned. Again, human presence was essential. At Tisani headquarters, the fusion of the structural expression and the digital fabrication techniques resulted in this building where the skeleton became kind of the skin of the whole structure. And here you have the robotic fabrication, which helped realize this actual parametric envelope. But it was the human craftsmen who installed and corrected these connections, adjusted anchoring positions, and made in-field decisions that allowed the theory to meet reality. So you can see right here on this video that the connections were used cranes to put these connections together, but they're humans. You can see the tiny humans here. They were there to adjust every millimeter, every centimeter to perfectly fit. And of course, we have the Burj Khalifa, which does remain the quasi-essential example of the terrestrial construction. and ambition. At this structure at 830 meters, it required an unprecedented buttress core system to counteract the wind loads and gravity loads along its height. The high-strength concrete was pumped at record heights. The crews work in very extreme conditions, managing thermal expansion, rebar congestion, and time-sensitive casting with precision and flexibility as well. And without these skilled labor forces, they were able to make these micro decisions minute by minute. This project would not have been possible. So these and many, many more structures represent this apex of human-led construction, which is precise, adaptable, and also inherently grounded in this shared understanding between the disciplines that I'm going to talk about later. So these constructions and buildings, they relied on presence of people on site, in the loop, and ready to respond to these physical realities of gravity, weather, material behavior, and very important, lack of caffeine. I know that very well. But this entire process assumes one thing, that we humans were there. So what happens when the rules change? Not just with the building codes that I will talk about a little bit later, but the physics, the materials, even the presence of the construction crew. For centuries, every structure that we have built so far has been grounded, literally and figuratively, except the IS said that it's kind of going around Earth. And we have these Earth familiar conditions, the 1G environment, 1G gravity, atmospheric pressure, weather patterns, readily available workforce, with tools and intuition that has been sharpened through centuries and generations. But Moon offers none of these. So what do we do here? There's no air to carry the sound. There's no water to mix the concrete, no weather to shield against. We only have the extremes. We have these temperature swings by hundreds of degrees between the day and night. The ground is coated in this ultrafine electrostatically charged regolith that, as you probably know, clings to everything. Gravity is only 1/6 of what we know. And if something doesn't align a site, what do? There's no one really there with a wrench or a torchlight that can just fix things up on site. Design can no longer afford to be conceptualized in this kind of an isolation, abstracted from the structural behavior or the buildability, the actual constructability of these structures. Every curve, every opening, every volume must respond to this internal pressure or lack thereof, if depending on what we're designing for and building. We'll have to address the radiation exposure, robotic limitations, and so many other ones. The actual traditional notion of expressive architectural form must now find its expression through performance and material efficiency. So we have to have a little bit different approach here. From an actual structural perspective, the low gravity may reduce the dead loads, which will probably be the case, but the lack of the atmospheric pressure introduces the challenge of internal pressurization, where structures might end up acting like balloons instead of our conventional way of here that we use to the columns and beams. And then compressive shell geometries become more advantageous, but also we have to worry about if they're printable, if they're self-supporting during structures, and so on. So this results out many different standard Earth-based structural systems. So we have to rethink those structural systems as well. And also, lastly, construction itself, it can no longer act. It can no longer be act as a skilled human labor guided by this intuition, experience, and improvisation as well. It has to become a pre-programmed robotic operation executed by the semi-autonomous or autonomous systems that do require a clear, conflict-free, probably buildable geometries and step-by-step sequences that are embedded in the digital models. So there's no margin for misinterpretation. And just to summarize all this, kind of in short that I just said in past couple of slides, is the design needs to inform the structure. The structure enables the construction, and construction constraints must feed back into design, not sequentially, but simultaneously. So the disciplines that we have separated here on Earth, you can see on the top here, we must now operate in a single integrated intelligence where the form, fabrication, and force, they act in kind of a one lockstep. So on Earth, we had the design phase, we had the structure, then we go into the structure phase where we do the analysis, and then we construct the structure. But on the Moon, we have to have a kind of a cycle, which doesn't mean it's a collaboration, but it more acts as a synergy. So as we step beyond Earth, so we're not just changing the location, we are rewriting the rules of every of these disciplines that I just mentioned, and in creating a new built environment. The Moon does not permit this luxury of the different disciplinary silos that we have here. The boundaries between architectural, structural engineering, and construction need to dissolve into a shared framework that's integrated, resilient, and hopefully robotic. And right now I'm going to cover each of these disciplines one by one, emphasizing their importance and what they cover and how can they further adapt into one synergy. So the role of the architectural design in extraterrestrial environments kind of is going to go beyond the mere aesthetics and spatial organization, even though it does still sometimes have that role here on Earth as well, but it needs to be emphasized on the extreme environments. It will be intended towards creating this environment that promotes health, well-being, and productivity in these challenging conditions, where light, space, color orientation must counteract these psychological effects in isolation and, as you know, sensory deprivation as well. Every cubic meter or feet, wherever, depending on what you prefer, must serve a purpose for habitation, storage, energy flows, or protection. And architecture will also need to consider factors as radiation shielding, large thermal gradients, gravity differences, atmospheric conditions, and many more. So additionally, the designs will need to maximize the use of local resources, whether the regolith is used for the construction, or we're using, for example, solar energy for power generations. And these architectural innovations will ensure that the lunar infrastructure, and hopefully the Martian as well, can support human life while also maintaining the comfort and functionality as well. So shifting gears now into the structural engineering concept, and structural engineering design on the moon is not really a variation of terrestrial norms. It represents a complete redefinition. Engineers must account for this internal pressurization against vacuum, prolonged seismic activity, protection from meteorite impacts, and a couple other ones that I'm going to mention in the next slide. And Earth-based codes don't really cover those. They don't account for such phenomena that are very different, nor for the 1/6 gravity, for example, which does alter the load paths, stability of the stability thresholds, and also deformation behaviors. So how do we do this? So to ensure the safety, entirely new design standard is currently under development by our AIAA Space Engineering and Construction Subcommittee for the Lunar Design Loans, and I think a couple of people from that from this group is on this call, so I can talk about this for another 2 hours, but this is not the topic for today. But basically, this initiative has outlined a recommended set of lunar specified load cases and combinations for the various structural systems that can be used for the various structural systems, including the dead loads, live loads, thermal, internal pressure, and so on. And in parallel, we are also actively identifying key knowledge gaps that, if unaddressed, may lead to a conservative over-design and inefficient design and over-designing for future construction. So bridging these gaps will be critical for developing these rational safety factors and achieving the structural reliability without the excessive mass penalties. The lunar structures will probably need to be designed around what the moon can provide. So we cannot just design for anything. We have to design what the parameters are there. For example, the in-situ materials, regolith, they aren't just a sustainability goal, they are a necessity. Engineering with regolith-based materials, doesn't matter what it is, like sinter blocks, lunarcrete, geopolymer materials, and so on. They require rethinking of the load paths, favoring the compressive forms, because I think some of you could know that they're very low in tensile stresses. Designing for brittleness, additionally designing for dust abrasion, while also considering fatigue limits, depending on different load cases. Optimization tools like finite element analysis and topology optimization will play a crucial role in minimizing this material volume while also maximizing performance at the same time. The new material models, which can be enhanced by machine learning, for example, are currently being developed to predict this long-term performance under thermal cycling, vacuum conditions, radiation, and a couple other ones. A perfect terrestrial example that I would just briefly mention here is that shows this practical use of the optimization tools is the 100 Mount Street building in Australia. SOM's engineers, structural engineers, have developed this innovative cross-brace exoskeleton structure. You can see right here on the exoskeleton on the facade, by using topology optimization algorithms and classical structural analysis as well. The tower is highly efficient, and the tower is very high, like efficient with its structural systems, and it has a very efficient exposed mega bracings that have been designed to kind of counteract the actual torsion response of the building, while also minimizing its size, cost, and very importantly for earth case is the carbon footprint of the bracing system. So there's so many things that have been addressed at the same time through this technology application. But we also have to think about, so even though the precision and the optimization do remain an ideal, it relies on environmental, material, and performance data that we don't simply yet have for the moon. So we still need this data, but we cannot make this ideal. So in the near term, the more viable and mission-aligned path is to deliberately over-design structural systems. So that might be that is my opinion at least, but yeah, let's see. So it's not really for elegance, but for survivability. Every lunar structure should and probably will prioritize robustness over efficiency, distributing the risk across redundant and sacrificial components. And these initial habitats may be heavier and less redundant, but they do offer a critical dual function, which is ensuring human safety and acting as a full-scale experiment. And they're probably going to be embedded with sensors, and they can generate long-term performance data that we need through those sensors on addressing thermal fatigue, pressurization, regolith interaction, and many more, which would pave a way for a smarter, lighter, and more refined design in the next generations. So in this approach, the failure of individual component is acceptable as long as the system preserves life and learning. So we have this dual efficiency here. Additionally, the lunar construction is not just what gets built, it's about how it gets built as well, which is very, very important in this case. With human labor minimized, the robotic assembly does take the center stage, as you can see one of the examples that we did with Princeton University here. And we did like a glass dome integrated with 2 robots, but humans were only integrated there to place the glue between each of the glass components. And this kind of alters the structural design from the outset. The components must be modular or could be modular, tolerant of robotic placement errors in this case specifically, and also compatible with the additive manufacturing or regolith-based layering techniques that we're talking specifically for the lunar environment. The low gravity and vacuum conditions also influence these construction sequences. We have to worry about stabilization during assembly, which becomes non-trivial. The structural elements may behave unpredictably without the Earth's gravitational compression. And these constraints demand a very kind of tight coupling between the structural modeling, construction simulation, and robotic planning as well, execution, sorry. And this ties in the last discipline that I'm going to talk about is robotic construction. On Earth, the construction is messy, but humans, we make it work somehow, right? This is, for example, you have here in the middle picture is you have a big steel brace that a human is trying to fit in together, even though we're still using robotics as cranes. On the left picture, you see the very congested rebar cage where these bars need to be fit in together. And on the right side, you see these workers that are just, there's a lot of them placed in the concrete, pouring the concrete and trying to see how everything fits in place and how they're laying out these components. On the moon, we might have a different approach. It must be clean, predictable, and machine executable. The lunar construction will most probably be carried out by autonomous and semi-autonomous robotics, teleoperated when possible, hopefully, but often working independently due to the communication delays, unless the humans are there literally in close proximity to operate these things. An example of a robotic slash technology slash human collaboration can be seen here all the way on the left, for example, which is the SOM's Angelus Novus Vault. I still don't know how to fully pronounce it correctly, so I'm sorry, which was constructed by humans and the virtual reality goggles and without any typical plans on site. So humans have put together this vault with just having a VR goggles and just without any plans, just stack the bricks together with mortar. We are also exploring ways of implementing computer vision in identification of the components during the construction phases or identifying damages that can occur during a service life of the structure. Also a very popular field is the additive manufacturing, which has been also explored through some of the SOM projects here. But this shift that we're using actual robotic, this changes everything, right? So robotic construction isn't then ends up to not be only about placing the material. It becomes about managing logistics, sequencing, and redundancy with really no hands on deck, because there's no hands to be on deck in this case. Tasks like excavation, regolith handling, 3D printing, additive layering, and so many different things, module assembly maybe, for example, they all must be programmed, simulated, and validated long before a single robot touches the ground. And as these boundaries, now combining all these boundaries together between the architecture, structural engineering, and construction, they kind of begin to dissolve in this lunar context when we talk about it right now. We are just not rethinking the roles, we are redefining what's possible. The traditional workflows that are shaped by human labor, terrestrial materials, and these gravity-bound methods, they no longer apply. We have to reimagine these. And with robotic systems taking over the actual act of building, we have a new design space, a space where structural forms are no longer dictated by these human constraints, but by performance, precision, and environmental necessity. And so this is the realm of the structural freedom through robotics, where autonomy, adaptability, and material-driven logic do enable new forms and strategies that were once unthinkable on Earth. And we might learn something new along the way as well, so you never know. So historically, construction has been defined by some of the constraints, which does include the human reach, labor safety, available tools and technologies, standardized materials, and so on. And some of these constraints are listed here on the left. So on Earth, these limitations, they kind of inform us not just how we build, but what we build as well. So they define our shape of the structures and buildings and any types of other infrastructure. We design for cranes, for scaffolding, for flat ground. So all these things kind of come together to shape our infrastructure that we have here. On the moon, these assumptions don't fully break down, but they do require further adaptation. The robotic construction does offer a paradigm shift, kind of replacing this manual limitations with programmable precision. Instead of being boxed in this by terrestrial constraints that are some of them are listed here, we can now explore these creative structural solutions that are custom fitted to this extreme lunar environment and hopefully Martian as well. I'm going to run through one of the examples that SOM did, and I don't remember what year. It was a few years ago. They did with the it's called the AIME 1.0 project, which is a result of collaboration between SOM, structural engineers here, and architects with the Oak Ridge National Laboratory, as I remember, yeah, which exemplifies kind of a balance between this design freedom and the materials / robotic construction in the 3D printed architecture. So while the robotic additive manufacturing did enable the unprecedented geometrical complexities, which you already know, we can have so many different shapes of 3D printing, such as integrated structural ribs. In this case, we have the airflow that is optimized for these curves, and combined building systems as well, which is very interesting. It has electrical, glazing, and structural elements within the single printed shell. The project still did face the constraints from the anisotropic properties of the carbon fiber reinforced ABS plastic. I remember because I used the ABS plastic during my PhD. And this material has its weakness in the Z direction, which is the vertical, and it did required in the end the steel tension rods for post tensioning. I think it's in the next slide. Yeah, right here on the left, you can see those post tensioning rods. So besides that, it had also the limitation of its printer's inability to generate the support material that is limited by these cantilever angles of 45 degrees in order to prevent slumping. So using these constraints, SOM has redefined the design workflows by embracing them and using topology optimization to align these load paths with the material's strong X and Y axis, while also leveraging the robotic precision to consolidate these traditional wall assemblies into a monolithic recyclable structure. You can see here, right on the right here. And this resulted in a 38-foot-long prototype demonstrating this zero-waste construction, bidirectional energy sharing, and also CAD-to-system approach that bypasses this completely conventional trade partnership between the design, engineering, and construction as well. So yeah, that was a really good example. But so right now, kind of combining the content that I talked about so far, I'm going to identify a couple of key points that that come out from this kind of a conclusion points in the end. But yeah, so we're designing for unconstrained, the design that is not constrained by human limitations. That's one of them. So in robotic construction, the workflows, it doesn't really no longer cater to human limitation. There's a possibility that we fully eliminate the human construction and all, or they minimize the scaffolding, the cranes, the formwork. So all these components kind of go away. Maybe not completely, but we can minimize in a certain case. And elements that typically shape the structural topologies on Earth, basically. Additional freedoms that are associated with the robotic construction these additional freedoms that are associated from the shifting from the human construction to robotic construction. Some of them include the actual robotic operations in lower gravity, nonlinear angles, non-pressurized vacuum environments where humans cannot really operate safely. They can fabricate on sloped terrains where humans cannot really access these pits and valleys while exposed to the radiation and extreme thermal gradients. And also the structure is no longer adaptable to the human builders. Instead, the builders is adaptive to the structure. And this mindset opens up the new door kind of to new design strategies that are driven by this material efficiency, not constructability. Another important consideration is the actual freedom from the traditional construction logic, which we are just stuck kind of even now on Earth. Even if we want to redesign new buildings and reinvent new buildings, we're still stuck in this traditional construction logic. But in this case, it needs us to allow for this new lunar structure to emerge into new forms. The topology optimized not only for the convenience, which it can be, but it's for physics and performance. So some of the structural components that could be designed to serve as a multi-purpose element would include the shells and bolts that do maximize the compressive strength and minimize material using of hybrid inflatables that balance the structural rigidity with the deployable volume, and buried structures that do leverage both the regolith for load distribution and radiation shielding. Just an example. I know there's many more here. So these topologies would evolve not from the aesthetic experimentation, but from the actual structural necessity and environmental logic as well, which have been tested here on Earth, but we're still limited by it, and we're still kind of constrained by the structural logic, as I mentioned before. So when we work with the ISRE materials like sintered regolith, just a perfect example, because I think everybody talks about sintered regolith right now, the geometry must align with the actual material behavior. The sintered regolith behaves like glass ceramic, as you already probably know. It excels in compression, but it's very, very brittle under tension. So thus the structurals will favor some type of arches, domes, shells that have these kind of curves that distribute these loads naturally, especially if we have lower gravity. Inflatable interiors do offer pressure retention, while some of the rigid shells, regolith shells, if we do have a rigid regolith shells, would act as a compressive components, protective components against the impacts and temperature swings, forming this hybrid envelope. So we can have this multi-layered structure as well. In the robotic construction, the material characteristics shouldn't be taken as an obstacle. They are kind of a design parameter. So we're trying to not think of it as a problem, but as an opportunity, which some of the partners love to say here. So I get it now. So in this case, form becomes a function of durability, efficiency, and also relies on the actual structural properties of the material. And so now I know I talked a lot about this, but I'm going to try to summarize everything kind of and see what the next steps are. So we're going back to the importance of the synergy, as I mentioned in the introductory slides. Construction is no longer linear, as I mentioned before. Disciplines, and it's not separated. We don't have these discipline-separated processes. It represents a tightly integrated systems where the design engineering and robotics must operate in this union and uniform complexity from the start. So unlike Earth, where disciplines work in sequence, lunar missions will demand a simultaneous coordination between the architect's structural logistics and also fabrication process. We need to have this seamless design to robot pipeline that is trying to replace this traditional back and forth workflows. There is really no tolerance for RFIs. I don't know if anybody knows what I think some of people know what RFIs is a request for more information when we are providing the plans to the actual construction crews. So they have a lot of questions along the way. So we cannot really have those, or we cannot have a lot of misalignments when the habitats are assumed to be autonomously built millions of miles away from Earth. We also need a real-time feedback loops between these digital models, environmental data, and also robotic control, allowing this system to self-correct, adapt, and maintain fidelity to achieve these performance goals or whatever we have envisioned. So just to sum up, is like synergy isn't really a luxury. It represents a foundation that makes the extraterrestrial construction not only feasible, but sustainable as well. So on Earth, is just a perfect example. On Earth, if we encounter some non-typical construction step, we do improvise, right? But please don't tell OSHA, so it's fine. But on the moon, the robots will stop. This focuses us to move from this reactive thinking that we have here on Earth, going by micro decision by micro decision from minute to minute, to a proactive integrated design where every part of the process informs the other. So the architecture must express the structure must reflect the construction logic, and the robot must execute precisely. So this represents the synergy that I've been talking about, not just collaboration. And as we explore these new structural possibilities unlocked by this new robotic construction, it is clear that this freedom in form is only made possible by precision and execution as well. So this is where the robotics move from being a tool that we're typically used to just being a tool. We're operating and moving things around and so on, but it's becoming a backbone of this extraterrestrial construction. We are shifting our focus from what can we build to how can we build it, examining these robotic systems, construction strategies, and levels of autonomy that will make this lunar construction not only possible, but scalable and repeatable, which is very important. So beyond enabling these non-traditional geometries and material strategies, robots will play a role of the primary builders, excavating terrain, printing structures, structural components, assembling the infrastructure elements, and so on. And I've just tried to kind of list out some of the most popular robotic systems that are currently out there that at least I know of, but I know there's many more. So I'm sorry if I didn't mention some other ones, but we have the NASA Apex rover, which will be capable of excavation, moving regolith around, very, very important, that is optimized for this payload weight, for the lunar soil, balancing this digging and digging efficiency and mobility as well. We have the Gaia lunar robotic with very high TRL, which is doing autonomous construction, like an inchworm robot, equipped with the grapplers. Both ends of the arm can be adapted to any type of, like a vehicle, rover, lander, satellite, and so on. So it's very, very useful. We have the very famous NASA's Armadas robotics, which assemble these voxels one by one and can form different geometries for solar towers, for rails, railroads, landers, and so on. And I know there's a lot of attempts that are going towards 3D printing, depending on what material, but they're still kind of at the lower TRL and need to be consistent to work in vacuum to provide for some good material properties that we can use for the design. At least that I know of, that are the data that is out there. So as we gather this current state of the art lunar robotics, this is not all of it. I know there's so much out there, and hopefully we can bring those higher up to TRL. We do have to think about scale, coordination, and repeatability. So this is very important, and especially if we want to have a sustained human presence. So we are moving into a space where the robotic must not only construct, but it must adapt, learn, and grow to be in this new built environment. And as we push these boundaries further, we must ask ourselves, are we designing the right machine or the right system for the machine to be built? So I'm going to repeat this question again, and maybe I don't know if I said it properly. So are we designing the right machine or the right systems for the machine to build? So that's an important one. So to fully harness this potential of robotic construction on the moon and hopefully Mars, we need more than just the physical machines. We need a digital backbone that connects the design, simulation, and fabrication in real time. As this construction becomes more autonomous and mission critical, the tools we use to design must anticipate the tools we are using to build, right? And some of the key enablers I try to list them here. At least from my perspective, some of the key enablers would include the parametric workflows that are linking the structure and fabrication process. Another one is emission-aware structural simulations that account for these lunar conditions, loading conditions, constraints, and so on. we are addressing the simulated construction environments and robotic path planning, very important because we don't have humans there to understand the load path. The digital twin concepts for mission planning and structural health monitoring. So knowing what the structure actually, how it behaves in real time. So while these technologies are well established in some of the robotic industries, as far as I know, their application in structural engineering and construction on Earth still remains limited. So we need to kind of first bridge this gap here and try to see how can we use this to build buildings that are resilient, efficient infrastructure that go beyond Earth, but also help us also develop some infrastructure here as well. So as we look ahead, the path of this lunar construction is filled both with complexity and promise. So I know I talked a lot here, but we do face some clear challenges. We have our digital tools that don't always speak the same language across disciplines, as I mentioned, architecture, engineering, robotics, and so on. We have communication delays that demand autonomy. There's no building codes on the moon, even though they're under development. So hopefully we can get them out soon. And also we're working with the strict energy and material constraints, all while relying on very limited real world data. So yet these very challenges do open more like new opportunities out there. We have to rethink them. We cannot just take them as problems. So we have to take them as opportunities. We can draw, for example, on bio-inspired designs. We can use machine learning to plan and adapt this construction in real time, and also maybe develop module design systems that can scale across missions and environments as well. As we build beyond, as we begin to build beyond Earth, hopefully very soon, we are not just exploring this architecture, we are reimagining it. And that's one of my favorite words right now. It's just reimagine this full architecture, because we cannot do the same things we're doing here. So the question really becomes here for everybody, I'm going to leave you with this, is what principles of design do we need to leave behind on Earth? So let me know. Thank you.
Awesome. Great talk, Nerma. Thank you very much. So we actually have a couple questions in the Q&A already, so I'll jump straight into those.
Okay.
Excuse me. First, Eric Franks asks, what are the first structures that will be built on the moon? Any ISRU or mostly assembly and outfitting of imported materials?
Is that two questions or one, right? Let me see.
Somewhat of both, 1.5.
The first structures, well, I can think of some of them, but well, as some of the landers have proven, we do need some landing pads, I think. And well, as I mentioned before as well, so I was always I'm gonna go back to the previous slide actually. So I always talked about, oh, we need more data, we need more data, we need to gather more information to actually start building. But after talking to several people that have been to space, I have kind of adapted my vision further and my thought process and said that we need to kind of look into structures that we can over-design them. We can have them try to see as, or we can just design a very rough structure and see what happens, like understand it. But we have to understand that it's that it can sustain human life for sure. It might be over-designed. It might take all these loads. It might not be very sustainable, but we have to learn from those structures. We can try to test it out as much as we can, but I think we do need humans out there as well to actually have that experience and try to see what experience they can run. So some of the habitable infrastructure would be very beneficial, even though I know a lot of robotics is trying to be out there, and a lot of robotic missions are planned. So I cannot answer what the first structures will be. I want to have several of them, but I think we do need the first supporting structure for infrastructure, for landing pads, for maybe top towers as well, trying to see how the assembly works and what we can learn from them. And then we iterate and we learn with time what is actually required. So that's the full answer is I don't know. It just depends what the mission, what the goal of the mission is. So, and the other part is any ISRU or mostly assembly and outfitting of or mostly assembly and outfitting of important materials. I'm not like do we more focus on ISRU or important materials? Is that the question?
Yeah, I think that, I mean, Eric can correct in the chat, but I take this question to be For those first structures, are we going to need significantly advanced ISRU technologies, or do you envision it being more, we bring it with us and build it there?
The dream would be to use the fully ISRU built structures, right? But we don't know that. So probably the first structures will be imported fully from Earth, and hopefully, I think NASA is developing some of them right now. And we need to test the regolith. That material might be different from the actual lunar samples that we have obtained from the Apollo missions. So we have to actually get the data to understand how can we fully implement it and maybe learn along the way, because we are in a different environment as well. So we can actually try to harness the actual environment that is there. For example, we cannot mimic gravity here very easily, but we can just go there and test it out. We have to jump through hoops to mimic vacuum conditions here, but on the moon, we just go out there and do it, right? I know it's not easy, but we still have to kind of test those in the environment as well. So hopefully, the first ones will be imported, but then as we learn more, we can expand it and hopefully go full ISRU, especially if we go to the Martian missions. Yes.
Well said. Thank you.
Mhm.
Next question comes from Francisco Chitty. Excellent presentation. The presentations seem to gravitate around above-grade structures. What about their foundation systems? Even though modular construction is expected, have there been discussions about what type of foundation system is expected to be used?
So I cannot talk about that right now because we're working on that project right now. We're analyzing some of the foundation systems. We're trying to see what we need actually. But as you probably already know, Francisco, which I know you very well from FIU, and civil engineer here, so I get it. Depends what structure we're building. Depends what loads are going to be there, and what we actually need depends on the purpose of the structure. So I would assume we would definitely need foundations. We want to avoid settlement. We have a significant seismic activity. We also have thermal gradients that will impact that settlement from a different perspective that we have here on Earth. So we will probably need the foundations. And but regarding the structures underground, I did not fully run into that full-on research yet. So I'll leave that question open for the underground structure people.
Awesome, thank you. Next question from Karis Cosmos. In the case of inflatable structures on the lunar surface, is there a standard or material of choice as regards the material for laminating the tensile load-bearing fabric? Is it possibly the same as for EVA suits? That's a cool question.
That's a really good question. And the actual material choice for the inflatables, I wouldn't fully know, honestly. I haven't done the full-on inflatables. My PhD was focused on the actual material there, like the regolith, and how do we use lunar polymer concrete. Some other research with sintered regolith and casted, but full-on inflatables. I know there has been research done, and there's some papers out there, but they're full material properties. I don't know. I know they have some issues with maybe radiation and thermal properties. And another important thing that I would mention from structural point of view when it comes to inflatables is to have a good support system. We have to understand how the structure fails, like the failure mode of that inflatable structure, how that's going to sustain if we have, for example, a puncture from meteorite, if we have a abrasion from the constant lunar regolith being exposed to it, if we have a EVA suit, EVA missions that go out in and out, so having these live loads that are depressurizing and pressurizing the structure little by little with fatigue. So some of the questions do have to be addressed in this for the inflatable materials, actually. But it's a very good question. I think that that research needs to be still advanced further.
Awesome. And yeah, well put. A very interesting question, and something I had not considered. Anyway, the next question. Nithyogopal Goswami asks, one principle of design that will be altered is compaction of regolith. My question is, how do we design for thermal and meteor loads? We can use numerical codes like FLAC 2D or 3D for regolith structure interaction. What do you think? And when you're done, I want to chime in on this too, if that's okay.
Okay, of course. I'm going to take in the how do we design for thermal and meteor loads, and I think you're going to take about the other one. Yeah.
Yeah.
So we are currently putting that into the lunar building codes. We want to call them guidelines because we don't have enough data yet. But we do have I'm not sure if I want to reveal too many things there because it's still under development. And we're almost done. We're putting a commentary together, but looking into the blast loads, looking into the environmental loads and how do we address them? Because here on Earth, we do design sometimes for thermal loads and thermal expansion and contraction, but not in the sense, not in that scale as we're going to do for the lunar structures. Like those gradients are drastic. So we have to look into the joint designs. We have to look how these members interact with each other. If one side of the habitats, for example, is fully exposed to the sun and the other one is not. So looking into this continuous structure being exposed by different thermal gradients also has to be taken into account. Looking into the thermal strains, for example, will be of interest. But we're taking it as a constant load. So we're not just taking it as we're taking one of the small cases in lunar construction. We're taking it as an actual case for the thermal loads and mirrored impacts as well. We're like kind of mimicking to a blast loads and also some of the parametric designs as well we have there. Analytic designs, not parametric, sorry. And Jared, you wanna take on the other part?
Yeah, I'm working on doing finite element analysis of lunar regolith for part of my dissertation work, and I've used FLAC 2D and 3D before. I'm currently using Abacus to do smaller scale regolith interactions with tools like a scoop, for example. And one thing that a lot of people don't realize is that the way the lunar regolith fails is really, really different than what we experience here on Earth. The strain softening and consolidation hardening aspects of the regolith are actually really hard to computationally simulate. Yes, finite element continuum methods are there's ways to do that in finite element. There's ways to get at it in discrete element using particle interactions rather than a continuum material. Both have significant shortcomings, and we are still working on actually being able to represent the complex physics of lunar regolith computationally and mathematically. So I think it's a great idea, but I think they all need to be taken with a large grain of salt and adapted, as Nerma pointed out throughout her presentation. So anyway, sorry to jump in with my 2 cents there.
Good. Yeah, and let me guess, we need more data.
We need more data. So I'll jump to the next question. Jason, I'm so sorry before we go to that. Parker Bradshaw pointed out, relevant to our last conversation about the fabrics. Parker Bradshaw pointed out one option is that you can make fabrics out of spun glass made of regolith. The company that is developing this right now is Moonfiber. So just
Very interesting
FYI.
approach. I like that.
Yeah, that's a cool
Read
idea.
into that. Yeah.
So thank you for that input, Parker. And now, Jason, back to your question. What are the major technological gaps which need to be overcome before engaging in large autonomous robotic construction operations? Assuming launch capacity from Starship, landing pads, reliable power generation, communications, transport, and compute power, which challenges require immediate solutions to create lunar infrastructure?
So first part, there's a lot of technology gaps, but first things first, we need to identify what infrastructure do we need right away. Like what infrastructure are you even designing for? You can like different construction different construction sequencing, different robotic systems might be used for taller towers and for landing pad or for a habitat or for connection different systems for rail loads. So we have to identify what infrastructure is first required in order to see what we don't know. So like we don't know yet what we don't know. So as we need to identify those, so we need to have those technical requirements set out first to know. But the second part, assuming launch capacity, which challenges require immediate solutions to create lunar infrastructure? Creating lunar infrastructure is one thing. Creating a lunar infrastructure for humans, for sustainable human presence, is another thing. So again, it ties into the first one: is what are the technical requirements? What do we need? How many humans are going to be there? For how long they're going to stay there? So we have a lot of things that we first need to set and have a design parameter, then we can understand what one infrastructure, how do we design for those, and what robotic capabilities we provide, and what we have here. And I know we still have a lot of technology development to do here on Earth, but we still first have to identify what we're building with this specific presentations that I had today. Is this synergy between the architectural, structural, engineering, and robotics. Is we need to first identify design parameters to incorporate all of those three disciplines into one to have that synergy. But here's like, you need a building. Okay, yeah, we're going to have how many people can fit in that building, because how big is the room? Okay, that's the live load. You go into the building code, you take that one number and you design it. It's not as simple as that, but it does kind of have that straightforward process. But in this case, we're still missing a lot of parameters that we need to design for. So I know that was a long answer, but I hope that helps in a way.
I didn't ask the question, but I think it was good. All right, and the last one that's currently in the Q&A, Karis Cosmos asks, do we assume 1 bar pressure for habitats in general, or can that be reduced?
I would point back to NASA references for that and what do we require. For me, as a structural engineer, NASA needs to give us this actual number and what do we design it for the actual human habitability. So we engineers can use it and design a structure for such a load, which would be internal pressurization load, which is also addressed in the design guidelines in the building code. So depends.
Awesome. Another one came in. Nithyogopal Goswami again asks, one idea is that we can use centrifuge to mimic the reduced gravity. And yes, centrifuges can create less than 1G acceleration. Just a thought. Wonderful presentation and hope to work together at some point.
Yes.
I'd also like to point out we do have suborbital and parabolic flight capabilities, but I did not know centrifuges could go less than 1G. So
me neither. But can we go above 1G? Can we use it somehow? I'm just like stating a question out there. We're always trying to mimic less than 1G, but what if we can somehow harness the technology that we have for like larger Gs and then use the material that use that to create materials that have this capability, have the material properties achieved through the larger than 1G. So just a thought out there as well. That was somebody mentioned that a couple of days ago. So I'm like, actually, yeah, we can have multi-purpose. Yeah. And
awesome. They just posted, I'm gonna put in the chat, everybody, a link to a NASA document pertaining to the physics of artificial gravity. If you don't have time to grab the link, you can email me or contact me otherwise afterwards. But I don't see, oh, I see one more in the Q&A. We'll take this one and then we will call it quits for the day. Jason Matthews asks, how do we go about site planning and site preparation? What types of machinery do we need to complete that step?
machinery, that's not my field, unfortunately. What was the first part? Sorry, I was.
Oh, sorry, I accidentally clicked out of it in the Q&A.
Oh, got it. How do we go about site planning and site preparation? Again, depends on the infrastructure that you need. How well do you want to prepare it for? We're looking into one of the project right now with NASA. How compacted does the site need to be? Do we need to achieve the same compaction as we have here on Earth? Does it need to be less or more? Like, what's the actual parameters there, and how do we behave this? How do we design for that? So we're still assuming we're using terrestrial numbers, but what if that number, what if those numbers are not really applicable for there at all? What if we don't have to achieve this? I don't know how much percentage of compaction and so on Earth here. So, and I think I know a person who knows that the most. It's Ian Jen, but he's doing his PhD literally on this, so he can hopefully one of the calls he's going to be here as well. He can talk about it more. But it all depends as well on what infrastructure do we require. So.
Well, I thought I saw Ian here and a couple others, Jason, if you're interested. Eric Franks is on the call. I know he is interested in site prep and does site prep work. There's also Chris Dreyer at Colorado School of Mines. Some of us here at UCF do site prep, and Paul Van Susante at Michigan Technological University also does some of this. Just to name a few off the top of my head. But anyway, Nerma, thank you very, very much for giving such an informative talk. I hope everybody learned a lot, and I know I did. So with that, we'll uh call it quits for the day. Thank you again for the presentation,
Well, thank you for
everybody.
having me. Yeah.
Yeah, of course. Thank you. Everybody, thank you for attending, and stay tuned for the announcement for next month's webinar. I'll plan to see you then and there. And again, I'll have the recording of this up available on YouTube within a couple days. If you need this or any information, please feel free to contact me, contact Nerma. Uh, Other than that, thank you. I hope you've had a great April, and we'll talk to you in May. Bye,
I
everyone.
will. Thank you.